Shall we get started? Okay, hello everyone. Unfortunately, this computer is positioned this way, so occasionally I may come back to here to use the mouse. And let's get started. Today we're going to talk about unsupervised learning autoencoders. Hopefully we'll talk about all those, but
oh my God!
But we may not be able to. We may not be able to cover all of them. So we'll see where we can get.
Access the slide later.
First, we need to talk about the basics. After that, we will talk about different variations of this model. As you see here, today we are talking about AE and DAE, meaning autoencoder and deep autoencoders. And as this shows, in general, there are shallow models and deep models. An autoencoder could be both deep, could be either deep or shallow. They are very
deep. Which one is shallow? This is shallow.
Right hand side is deep. The left hand side is shallow. As you see, SVM decision tree boosting. Closely related to autoencoders are restricted Boltzmann machine (RBM) and deep belief networks (DBN). We're not going to talk about them today, but they are also very useful.
DBM
I know what those mean.
Yeah.
Those are more kind of popular, well known than that one. First, let's recall what is PCA. Does everybody know PCA relatively well? Okay, so then I want to make connection between PCA and autoencoders, and this seems just to be the algorithm. And what needs to be highlighted is that you are essentially projecting your data points onto a new subspace defined by the eigenvectors of the data covariance matrix. And those new bases come from the eigenvectors, which are orthogonal to each other. Right? So this slide is important because we are going to use the loss function of PCA to make a connection between this and the autoencoder. Essentially, PCA is also minimizing the error between the projected data and the original data X. And in this case, you can view each red point as your data point, and you are doing dot product between the eigenvectors and the original data point to get a projection, which is Z. And in autoencoder, I would argue that it's very similar. So let's make a connection now. First, before that,
one thing that I want to make sure is that the SVD.
Right.
So SVD, oftentimes, so if the data is kind of not around the origin,
right,
it's somehow far away from the origin. The data is clustered there. And what SVD finds is this direction. That is what it finds. So in order to make SVD work very well, what you have to do is we have to center it. So that is one of the very critical components to make SVD work. Right. I just want to make sure that this one is not centered around the origin. So this will not do very good.
This is very good because this is
really
pre-processed.
Yeah.
Okay. This is a common technique. Right. Thanks for that. And now we have autoencoders, and we want to make a connection. And here, the connection is that autoencoder is approximately PCA if we restrict autoencoder to only use linear activation function. Usually we have nonlinearity in neural networks, but if we only use linear activation, then they are roughly equivalent, and I will show why. Well, first, this is the basic structure of autoencoder. And if I want to be precise, autoencoders are essentially unsupervised neural network architectures that are used to generate a meaningful representation of the original input. It usually consists of the encoder and the decoder. In this case, the encoder is this layer, which maps original input, which is 3-dimensional, into a hidden version, which is 2-dimensional. And the decoder maps it back to the original input, 3-dimensional. So there are two layers in this model. The loss function, as defined at right-hand side, also minimizes the difference between the reconstructed input between this and the original input. So their loss function is equivalent in this sense. However, because it uses different way to optimize it, it uses backpropagation typically. it may have different results. In this case, as you see here, we are defining the weight matrix W and the weight matrix V. And the encoder is essentially the function f, which transform x to z through the W matrix, W times x. And the decoder is V times z. And if you rewrite this objective function by replacing the reconstructed input with the functions f and g, you will get x minus v times w times x. This is the encoder and this is the decoder. Assuming they are linear. In other words, in the objective function form, they are equivalent. Again, this shows the detailed description. So this is the original data, the red dots. And you have, in this case, a weight matrix, which is W, has two rows in this case, each row corresponding to your new basis. You're also doing projection by doing W times X. There is some slight difference. For example, there's no guarantee that they are orthogonal to each other, unlike in the PCA case, because the eigenvectors of data coordinate matrix are guaranteed to be orthogonal to each other, because data coordinate matrix is positive semi-definite. Is everyone clear with this? Do you have any questions why they are roughly equivalent?
Just very minor thing.
Okay.
The optimal solution is PCA. That is incorrect. PCA is unoptimal solution. You know.
That is okay. That is not okay. This is not my slide. This is from Toronto, CS department of Toronto.edu.
Yeah.
Anyway, thanks for pointing that out. Yeah, you're right. Okay.
Does it mean that V times W equals to I?
We'll talk about that in great detail later. Thanks for pointing that out. But the short answer is it could be, but we don't want that to happen. We will use some regularizer to prevent that from happening. Because if that happens, that violates the goal of learning meaningful internal representations. We will talk about that later. Any other questions? Okay. So they are not necessarily orthogonal. Again, this is using some real data set in 3D. And if you use PCA or if you use autoencoder, they should, in theory, get the same result like that, which is a 2D plane preserving the maximum amount of variance in the data set. You could have many internal layers, actually. So here, you could have different layers. So it's a deep autoencoder. But as long as you don't use nonlinearity, they are the same. Any other questions? No? Okay, so what if there is some nonlinearity? Then you would have this activation function around the W times X. In this case, they are assuming that V is the transpose of W, as what you pointed out. If they happen to be the case that V times W is identity, here W transpose times W could be identity if there is some property in W. So sometimes people would use this notation to indicate that you can use the transpose, you can tie in the weights of the encoder and decoder so that they are essentially the same matrix, just with a transpose. If that happens, this slide claims that we're essentially doing nonlinear PCA. There are some subtleties, but in general, this is an accurate description. So why not just use nonlinear PCA? Why do we devise this autoencoder? That is a question. And it turns out that the answer is that they are more flexible than the original PCA. You can not only add nonlinearity, you can do many other things with it. We will see. In this example, you can stack autoencoders to form a deep network. You have, in this case, you have 4 layers. The original input, layer 1, layer 2, you get the embedding, and then decoder, layer 1, layer 2, you get the outputs. Any other questions? So this is another representation which will be useful in a later slide. Just do it horizontally, nothing different, but it will be useful later. So it's stacked autoencoder. Here, come back to your question. Our goal is to learn meaningful, useful, hidden representation. Sometimes we call features, sometimes we call it patterns from the original data automatically using autoencoders. This avoids feature engineering. But fundamentally, why does an autoencoder work? If they just simply learn the identity mapping, why can't an autoencoder simply copy input output through identity functions? In this case, f and g, input and is the encoder and decoder. And you are minimizing x minus g of fx. What if they are both identity functions? In this case, let's make it overcomplete by adding two dimensions in the hidden representation. Both the input and output are 6-dimensional, and the hidden is also 6-dimensional. In this case, it could learn identity functions. In this case, you are not learning anything meaningful. You are just copying the input to the hidden representation. So this is something fundamental that we want to fix about autoencoder, this vanilla version. Is there any questions? Okay, so to achieve feature learning, people make it very explicit. This is a textbook, a famous textbook by Goodfellow, Angel, etc. So they say that autoencoders are designed to be unable to copy perfectly. Usually they are restricted, regularized, modified in certain ways that allow them to copy only approximately, because this model is forced to prioritize which aspects of input should be copied. It often is used to prioritize the data. It is a very high-level idea. Before moving on to how they do that exactly, is there any other questions? Okay. So here, one way is to make it undercomplete. Overcomplete means the dimension of the hidden representation is either equal to or even greater than the dimension of the original input. In this case, it is undercomplete because it's 5-dimensional. You can make it. You can go even further by making it only 1 dimension. Hopefully, that solves the problem. But it turns out that it doesn't usually work quite well. The intuition is that if you could only speak a few words per month, you would probably try to make them worth listening to by constraining the hidden dimension. However, the potential problem, as this book points out, is that if encoders or decoders are too powerful, they have greater capacity in learning f and g's, then it may end up being something like this, which means that your data points are mapped to this 1-dimensional line, which is 1D here, but the decoder would map it back. And if the 2 points are very adjacent to each other, they could still end up very far away in the hidden representation, which is not a good thing if they are very powerful. Here it's very heuristic. So I think the definition of powerful or great capacity means you don't regularize, and your f and g could be anywhere in your entire function space. It could be any function. So that's the intuition and the downside. Is there any questions? If not, we can look at other ways to do it, which is nowadays very common. You can regularize them through some additional terms in loss function. That's the general idea. Regularized autoencoders use a loss function that encourages the model to have other properties besides copy input output. They usually include the sparsity of the representation, meaning you have a lot of nearly 0 in your hidden representation. We'll see this more in a later model. Besides that, you can have smoothness of the derivative of representation. We'll see this later as well. Or robust noise or missing inputs. A regularized autoencoder can be nonlinear and even overcomplete, but it can still learn something useful as long as we restrict them in this way, in these certain ways. During the past 10 years, from 2018 to today, we have many different architectures. These are just representative or relatively popular ones that I want to talk about today. Essentially, it's just new ways to regularize the autoencoder architecture. Any questions? Okay. I will show this later. Yeah, but if you want to learn, if you want to get a hello idea, if you perturb your input a little bit, you want the representation to be close to the original input, robust to noise. You can use that way roughly. Here are some properties. So we will see why autoencoders work through thinking about what are the ideal properties of encoders, and then we'll look at applications of them, which are what most of us care about, I guess, the application, how you use them in research and real world. And here, this is some good intuition. Which of the following number sequence do you find the easiest to memorize? If you are autoencoder and this is one data point consisting of a bunch of numbers, and this is another data point, and you are allowed to map them into some hidden representation, which would you find to be easier? Essentially, you want to try to find patterns. Although this looks like shorter, but there's no pattern between different dimensions of this data point. But here, you do have divided by 2, multiply 3 plus 1, divided by 2. And every time if you see even number, you divide by 2, otherwise you times 3 and plus 1, something like that. So this is the high-level intuition. Hopefully you get that. So that leads to the first good property. Ideally, we hope that there are useful features. Some people say autoencoders are the climax of neural network deep learning because they can do representation learning. They capture the intrinsic properties so that we can feed those features into downstream applications. They can be thought of as patterns in data, so we can use this pattern to generate new data. Once we memorize this pattern, divided by 2 and plus 3, we can start with some random number, say 9, and then generate a new sequence that is very close to that in the generative setting. That is high-level intuition again. Second property is that this hidden representation should have lower dimension than input, because that leads to more efficient and compact representation, good for storage downstream models, and maybe free of noise because this is lower dimension, and maybe easier to visualize. So those are the good properties. And we will see one more before we stop for questions. Third property is that they should be very flexible, can be modified in different ways. You could modify input data. For example, rather than feeding the original image, you could add some noise. Hopefully the decoder could remove the noise. So you hope to achieve image deblurring, something like that. Second thing is the output data. You could try to reconstruct something different. They're actually counterpart to each other. So the third one is architecture. Rather than using fully connected layers, you could use other layers to capture your input better depending on your specific input. And we'll see that. The next is the loss function. As we see, you can add additional terms to regularize it. Sometimes they are related. The next one is you can modify the latent space. For example, we can enforce a Gaussian prior on the hidden space, usually through additional loss terms. This is actually a very popular thing nowadays, I think. Some of my colleagues, their research last quarter, working on debiasing word embeddings. They look deeply into the individual dimension of the word embedding and try to do something. So analyzing the latent space or the representations in the latent space, I think is a popular trend nowadays. They could do many useful things. Arithmetic operations, linear interpolations, generating new data, etc. Any other questions before we look at their applications? Okay, so here's what Ian Goodfellow said on Quora. So 10 years ago, people like him probably thought that deep neural networks would also need an unsupervised cost, like the autoencoder cost, to regularize. Here, deep neural networks don't only refer to autoencoder, could be any supervised model. People believe that.
Unsupervised cost. What is an unsupervised? I don't know what that is.
I will show you later on the next slide. High level, something similar to autoencoder. Essentially, you want to learn the features first before you can predict whether the image is cat or dog. You want to first extract the hidden representation through autoencoder, something like that. Today, we know that we can just use backpropagation along with many techniques, tricks, to train a big neural network. Given that we have enough label data, ImageNet. Right? So that is what we know today. There is something going on in between. So autoencoders fell out of fashion because we can just train them through backpropagation. However, they are still useful. They're not the fundamental solution to training deep neural networks that people thought they were going to be. So this is a brief history. So some people say it's a failure or it's not that useful, but there are still other tasks, new emerging tasks that they could handle well. And this is some thought I have. So humans can learn from very few labeled examples. It seems that we are just using big data to solve some predicting cat or dogs. So why does that happen? One popular hypothesis is that human brains, or mammal brains in general, they could leverage some unsupervised or semi-supervised learning. So this is another reason that this could be potentially very useful in future because this belongs to unsupervised learning. Any questions?
Could you go back to the previous one?
Oh, okay.
Yeah, for the 2C,
Okay.
free of noise.
Okay.
So I don't quite understand what that is. Does it mean like the presentations doesn't have too much noise inside of it?
This is just an intuition level because you have lower dimension. You don't allow the original dimension because, for example, the image could be 32 by 32 or something like that. But the hidden representation is very small dimension. So ideally hope that the noise is removed in the hidden representation. So if you sample a point in the hidden space, that doesn't contain the noise. That is done through, of course, if you just hope that won't happen, you have to do some tricks. For example, you have to modify the output so that you reconstruct the noise-free version of the input. So, yeah. Okay, this is just a property, intuition level, and you will see at the technical level how that is achieved. And I think here is really important. Some people care about application, most of us. The first one is data compression for storage, because they could provide more compact representation. You could store this on your disk more efficiently. However, they are difficult to train. Autoencoders are more difficult to train because a rule-based algorithm like JPEG could work better. Because autoencoders are very data specific, you need a lot of training data to have good representations. If you have some unseen image, you may not be able to generate that. So if your data is only about cat images, and then you want to compress dog image, it might not work that well. So that is a big issue. So that is not very encouraging. But the next one is pretty encouraging. The next one is visualization. From the dimensionality reduction point of view, autoencoders could do very well. So our baselines could be PCA, Tessini, or other dimensionality reduction techniques. However, for example, Tessini is good, but it typically requires relatively low dimensional data. Remember the curse of dimensionality. For high dimensional data, people argue that they could first use autoencoder to map it down to some relatively smaller dimension, and then further use Tessini to visualize it. And more interesting than that, you could have something like this. You could visualize your latent space directly, which I think is a very hot topic nowadays. You could do arithmetic operations. If you embed your images into the latent space and you do vector addition, subtraction, you could get this. This chair minus this chair plus this chair would end up with something like that. This is what people confirmed. 3D object embedded. And you could also do linear interpolation. I will explain this in more details. Basically, once you embed your image into the latent space, you could sample one point and sample another point, form a line segment, and you move from one point to another one along this segment. And each point, you use the decoder to generate the corresponding image. And this is the result you get. It smoothly transitions from the chair 1 to chair 2. This is cool animation, so that's what people have done.
Is it TSA already a tool that is useful for visualizing a high dimensional data in low dimensional? So why do I need to first use an autoencoder to convert it?
This is what people say. They say that typically it doesn't work well in practice on extremely high dimensional data.
But itself, it is a dimensionality.
Right. It's just any questions? Thanks. Okay. Next part is actually unsupervised pre-training. One of my colleagues did an interview, and the interviewer asked him what is unsupervised pre-training or autoencoders. So this is something people still care about nowadays. Let's first say there is something called greedy layer-wise unsupervised pre-training. I'll explain this term in picture first. So rather than training a deep neural networks, for example, deep autoencoders, by backpropagation like that, you could break it down into different stages. And each stage you train just one layer. And here is 2 layers. Each stage you train 2 layers. And the next stage, you train the middle two layers. And the third stage, you stack them together like an assemblage. And the second stage uses the output from the first stage. You feed that into the second stage input. So this second stage reconstructs this features learned from the first stage. Why do we do this? What's the motivation? One motivation is that because it's very deep, it could be the case that there is vanishing gradients once you backpropagate all the way to the inputs. So the gradients around inputs could be very small. By doing this way, you could address that. This is a very old technique that people discovered. And they used to use something like this to train a deep neural network. That hopefully address your previous question. And what is the downside? I think the first downside I can imagine is because each phase you need some parameter tuning. If suppose you already tuned this a lot, and at the second stage you realize that you need to retune the parameter because this is not good for the second stage, then you could go back to the previous stage. That increases the amount of time researchers need to do to tune those type of parameters, which is not good. Second, because it's greedy layer-wise, you may not achieve optimal global solution. So there are at least two downsides I can think of.
So is this related to unsupervised code? Or is it, you mentioned about unsupervised code, right? So is this related to unsupervised code?
Yeah, because you minimize the difference between the outputs and the inputs. You hope that output is as close to inputs as possible. That is the unsupervised cost. You don't have external label like cat or dog. That would be unsupervised cost. Supervised cost means you have dog or cat. Before you do anything about the cat or dog, you first do this, and then you may stack some additional layer on top of that to predict whether it's cat or dog. That is old technique. Nowadays, as I said before, we have big data set, ImageNet. We have random weight initialization, review activation functions, dropout, batch normalization, residue learning, etc. They are all tricks people use to train deep networks. That is another reason why this is no longer popular for training deep neural networks. However,
I'm still confused why they need three different phases.
Phases, you mean this one?
Yeah. Why we just need one?
One at the end. You mean why not just do this here all at once?
Or just need the phase one? Enough.
Because we want to project into. Okay, so later we want to remove hidden through and outputs. I should correct that. I said on top of it, but actually not on top of it. You want to remove hidden through and outputs. Use that as input to some later layers for classification.
So here the goal is we want to train a deep neural network. That is our goal.
Okay.
So, but 10 years ago, training deep neural network didn't work because of the gradient, vanishing gradient, right? So we tried to train it. Once you backpropagate maybe 2 layers down, there is no gradient, no errors to backpropagate, so it didn't work. So this is the technique that people use in order to get around the problem. So how do they get around the problem? They first train the first layer using whatever function and try to train it, right? And they use that as kind of initialization. So, and then on top of it, they put another step, and then they train it there. And then on top of it, they put another step, and they train it there. Once they have this good initialization points, then they backpropagate from there. So that is how they somehow minimize the training time. Otherwise, it will just take forever. So I think it is a variation of that.
So it's better than directly using the hidden two in the phase one. The size of hidden two as for the hidden one.
Say that again. I don't understand what you're saying.
Just using the origin hidden two to put it into the phase one to replace the hidden one.
You mean why have two phases rather than directly go to why gradually reduce the dimension rather than just when one shot we reduce it to say 100 to 2, something like that? Because I think
Is that your question? Oh, then it doesn't work because if we have only one layer, so when you have 2 layers, we assume that there are these non-linear transformation that we do at every hidden layer.
Just
So
adding more layers to make it deep.
yeah,
To
just make it
deep,
deep.
to make
Yeah,
it deep.
the same justification for making deep. Okay, thank you for pointing that out. So now they are still useful. That being said, that's useful in certain cases. And here is what I think. First, when you train a deep autoencoder, you can still use this technique. This is argued in some of the textbooks. So you can still use this to train autoencoders. Second, you can train autoencoder on an unlabeled data set and reuse the lower layers. Lower layers mean layer 1 and layer 2 to get hidden representation. You can reuse them to create a new neural network, and you train that network on the labeled data, which is usually a subset, because unlabeled data is cheaper than labeled. And closely related to that is supervised pre-training, which I also talk about. So there are, I think, important techniques, I think. So this is what it means. Unsupervised pre-training for supervised tasks. You copy the lower layers, and then you attach some fully connected layer softmax prediction and you do back propagation. So first train the autoencoder using any technique, maybe this technique, or just train back end to end. And then second phase, you do classification. Closely related to that, so this is unsupervised, which is the same thing. Closely related to that is supervised pre-training, which is more popular. So people already train large classification networks on large data set like internet, ImageNet, and you download their model architecture and their parameters online, and then you freeze these weights, and then you attach some layers for your own task. And then this is the popular technique. Hopefully, you've heard of that. And even closely related to that, there are concepts like, I'm not going to go into details, you can read it later, like transfer learning, domain adaptation, and multitask learning. And supervised pre-training is something like transfer learning. Inputs are similar, but your labels are different. Here, maybe they are predicting cat image, and here you may want to predict dog image or something different. So closely, belongs to transfer learning, which is another hot topic. And there are also other hot topics like one-shot and zero-shot learning. Hopefully, we can learn that someday in detail, or you can do it yourself. So that is the second usage, unsupervised pre-training for supervised tasks. The third one is you can train autoencoder on an unlabeled data set and use the learned prime representations, use the embeddings and feed them into downstream tasks. The idea is that if you just feed the original input to the downstream task, it doesn't yield very good accuracy. If you first transform your data into hidden representations through autoencoder and then feed it, you could get better performance. That is intuition. For example, use the classification. For example, if you have, let's just jump to that for example. Very good question. Word embedding, graph node embeddings. For example, if you want to classify, if you have a social network, you want to classify each user as one of several possible classes. If you feed the original input representation, which is a agency matrix, that will be a very large embedded matrix, consisting of a bunch of zeros and ones. They encode the connectivity structure. But if you first compress each node into a lower dimensional vector, that could capture the similarity between users better. That is intuition. So this is what some of us know very well and do research on. Word embeddings, usually the initial representation is very bad, one-hot representation in your vocabulary. And the second condition is that there is a lot of unlabeled data. We have a lot of text on the web. So that is when word embeddings work very well. You could also do image embeddings, but people would argue that images already lie in a rich vector space, where the similarity between the pixel values gives some meaningful things. So there's maybe no reason to do image embedding. However, recently there was actually something called LA Hacks 2018, where people in Los Angeles gathered here to do some weekend competition, programming competition, and one of the winners did a project on puppy image embedding. So you can check it out. This is very hot. This happens last month, something like that, end of March. That is the first winner. Remember the undergrads, so they also use something like TensorFlow to build this. And they can do some cool addition or subtraction between image puppy dogs and answer the question like, what is the similarity between one dog and another dog? What if you combine them? Something like that. So it's still useful. And this one, semantic hashing, you could turn database entries, text image into low-dimensional and binary codes, and do query, information retrieval in general. So these are just some representations, just some picture illustrations. You could just directly use it and feed into downstream tasks, or you could do something like a database search. You could first train your model on the entire database, turn everything into hidden representation, and then you have a query. Because it's already trained in the first stage, you can just run that query through the lower layers to get hidden representation, which is very fast for a query. And then you can directly compare those hidden representation. There may be some trade-off between accuracy and speed, but hopefully the speed is more important, and you get some good speed performance efficiency. So that is mapping hashing. Is also something classic. People already tried a lot on this. And there's actually something fundamental. If we have a lot of labels already, is there any reason to use a decoder? Why not just use an encoder and attach some fully connected layer on top of that? Is there any meaning to still use autoencoder architecture with the reconstruction loss? I think if you already have a lot of labels, then this may not be a good solution. So it's not always the right solution to use autoencoders. You need to have very poor initial representation, and you have a lot of unlabeled data. And your labeled data is very limited or something like that. So there are certain conditions you need to be aware of to use this. And the next part is very important nowadays, generative modeling. You want to use variational autoencoder and adversarial encoders, etc., to generate new input images, which we will see a lot later. This is also a hot topic. You could do some creative application for small kids, artists, other people, using this idea of generative modeling. And next, we have the final, almost the end. So we have self-supervised learning. It belongs to supervised learning, which means the targets or the true labels come from the input data, but not the same as input data, slightly modified. So this is another way to look at autoencoders. They are self-supervised learning models. So they are not really unsupervised. If you think about this, you still need some loss function. The loss function comes from the min-max, the difference between input and output. So the actual true label is the input. And here we can extend this idea to something else. Like we could, this is what I said before. You could predict. You could try to reconstruct the noise-free version. So in your training data, you have both this and this, and you feed this as input, and you want to predict as output. And the autoencoder should minimize the difference between the clear input and the clear output. This noise is added in the middle, so which we'll see later in more detail. The recent paper is using that to do jigsaw puzzle solver in the computer vision literature. So you can read this more later. So there are many cool applications if you slightly tweak the output and do something else. And here I think it's something interesting. And this concludes the first part. And then after that, we will look at different models. Let's think about other representation learning techniques, such as word embeddings, speedgram in word-to-vec. Why is speedgram more popular than autoencoders? You rarely hear of people using autoencoders to word embeddings. You heard people using that to do node graph embeddings. And why is that? What do you think? I have my own thoughts, but do you have any idea why that matters? I think I can think of 3 easy reasons. One is that it's simpler. Speedgram is easy to understand. It's also very efficient. And it works well already in the NLP application. People use this a lot, and they verify experimentally that this is already very good embedding. So they don't want something complicated, like autoencoders.
I have a question. Is it a speedgram autoencoder?
Yes, I will see that. You are very right. Good insight. I will see that at the end. I will see that at the end that they are essentially autoencoders through some tweaks if you do some mental exercise. And before that, so please hold that. So the second question is that when does a speedgram no longer suffice? That no longer suffice, you have additional goals, such as we want to do data denoising. Then speedgram certainly can do it well, can do it easily. Next, if we want to capture complex characteristics in the word, or we want to capture different meanings of the same word, called polysemy in NLP, then we can use some bidirectional STM with attention as the encoder. In this latest paper, 2018, deep contextualized word representations, they use this to do word embedding. And they figure out that if they use this one, and they use the word embeddings, feed that into QA pipeline, question answering pipeline, they will get a huge performance gain over just use speedgram models. So this is a potential direction in the future.
Just use paper from the University of Washington, or that is not.
Not quite sure. I'm not expert. I got this I got this recently from a colleague. So he recommended me to read it, but I just have too many things to read at the same time. So I just give a pointer to you so you can read it later. There's a future direction, I think. Yeah, in other words, this can solve a lot of problems nowadays. LSTM, if you need information flow, you have attention. And those tools combined can solve a lot of NLP problems. But it's still, we can think of it as some autoencoder framework. It's not exactly the same thing. The third one is generative setting. If you want to generate new data, you have to use something autoencoder or some other generative modeling techniques. Inductive setting, if you have unseen words, although this is not very common, usually you have a big vocabulary containing all English words. But suppose sometimes you have unseen data points and you want to embed them. Then for skip-graph model, it's not easy. You have to perhaps retrain. But in this autoencoder setting, because you already trained the mapping function, so the important part is that in the autoencoder, you have this mapping function, f, mapping from input to hidden representation. Once the train is frozen, and you can feed in any query. So that is the advantage of autoencoders over that. Yeah, and the final question is what Professor said. Can skipgram be viewed as a special case of some autoencoder model? After Googling and thinking myself and discussing with some colleagues, we think that it could be. What do you think? And you need to recall what is skipgram. Essentially, we are trying to reconstruct the words, right, around a certain context window. So for in this sentence, if we take out this word, we have a window, maybe 1, 2, 3, 4, 5 word window, and you want to skipgram is like use this word to predict the surrounding words within this window. And if you think it's as autoencoder framework, although you need some mental, it is not easy to see, but you can do that later if you want to clearly see that. I encourage you to do that. Essentially, you are reconstructing the window. Any questions? I know this is not super clear, but hopefully you can.
Here, when you say denoising, what do you mean?
Deep learning, like if you have some noise in your data, for example, like this.
So image I understand.
Okay.
Image there. But text, what noise am I?
Not that common. So this is what I mean in general. Okay, so this is not like skipgram versus autoencoder. So this is what I mean is that when you want to do something fancier, like easier models, like skipgram no longer works. Windows no longer work. It's not necessarily NLP. So sorry about that. Okay, hopefully that clarifies. I'm more thinking of image in this case. Okay. Any questions before we move to the next part?
What is? Oh, so inductive setting is embedding unseen words.
Oh, right. It's rare, right? Yeah, usually you have a big vocabulary. But it's useful in other areas like image or graph, or audio, or something else.
Polysemy.
Okay. Polysemy. It means one word could have multiple meanings, like Bush could be either last name, right? President
But
Bush,
that one, I don't think autoencoder will solve the problem.
It's not nothing. It's bidirectional LSTM with attention, as the encoder would solve it. That's the point of this paper.
I see. So by encoding the context together,
Right.
so it's now it is no longer mapping one word into one particular vector. It's more of like encoding the entire context into a vector. Because the reason why I'm saying that is because if every word is mapped into a single vector, then it doesn't solve the polysemy problem.
I understand.
Only when a word is mapped into multiple different vectors, then you solve the polysemy.
Multiple embeddings.
Right.
Okay. Yeah, good point. We could look into that more. Any questions? Okay. First is the sparse autoencoder, which appears in a lot of textbooks, and it's a very classic technique. And it has a lot of good intuitions early in 2008. First motivation is that something called sparse coding. Intuition is very simple. If you have an image, it should be represented by only a few base images. Base images in this case are something like this, just a bunch of edges. And in this case, this particular image could be decomposed into only 3 base images. It shouldn't be a lot. So the coding here should be sparse. You have 3 non-zero entries. That's the basic intuition. That is a very old thing, I have to say. For text, it's similar. You'll have only 3 topics. LDA, LSA, things like that. You have 3 topics in this case. And here, matrix level representation, you have to, okay, so the task is that we are given a training data set X. We want to learn a dictionary D and sparse code alpha. Back then, they didn't use the terminology we use, like weight matrix. But essentially, this is a weight matrix. Okay, so we'll see that why in the next slide. And we hope this sparse code, which nowadays we call embedding or representation, to be sparse, this alpha. So in this representation, hope it's more clear. But essentially, the D matrix, the dictionary, is the weight matrix we want to learn. We want to learn W transpose X is alpha. And we want to, in the decoder, we want to use D alpha is back to X. So that's what Joey said. They could be, DD transpose could be identity matrix. That is fine. Yeah, so that is the basic intuition. And the additional thing is that we want this to be sparse. That's the only difference. We call PCA. We don't have that constraint. But we can also look at it as a change of basis or projection. Nowadays, if you look at neural networks, it's also similar. We just replace D with W and alpha with the hidden representation H. We don't want that to be identity function, so that is the motivation number 2. We want to prevent identity function from happening. So how to do that? You want to make sure that H is not the same as X. If this identity, H is essentially the same as X with a bunch of zeros at the end. So this part is same as X, and here you have some zeros. How to prevent that? You want to make sure that this is sparse. Have a lot of 0 entries, because X probably is not sparse. It has a lot of different non-zero entries, and you want this to have a lot of zeros. That is basic intuition. And actually, another intuition is from human brains. People working on neurobiology or something like that figure out that human brains have something similar, sparse coding, which I'm not quite sure, but you can encourage you to learn more. Let me finish this before we pause for questions. For image case, you don't want them to be identity matrices. And one additional thing I want to mention is that in this case, your learned dictionary or weight matrix W is essentially equivalent to convolutional filters in the convolutional networks. We can think of the W matrix as a bunch of convolution filters, each with the same size as the original input, which is 4x4 in this case. You can imagine this to be 4x4, but it's not. This is just an illustration of the idea. W matrix is a bunch of 1s and zeros. This is something bad. We don't want the 16 columns to be just a bunch of 1s and zeros over there. So that is something we want to prevent. And this is very useful later for visualization, because once you understand that the weight matrix can be thought of as convolution filters, you can directly plot each individual column in W and see what it looks like. That is similar to the idea of convolutional neural networks visualization. The difference is that the convolution filter is the same size as the input. So it's more like a feature detection. Or it's just a, or you can think of it as a convolution filter. In the case of word, just okay, sure.
So W is really a flattened out matrix, right? So W, the dimension will be
16 by 16, and each column is you can map it back to a 4x4 vector.
4x4. So,
yeah, so you vectorize each image into
vectorizing
16
it, right,
dimension and
right.
multiply by
Yes, yes.
Okay, thank you. And for the document case, you don't want this to happen. You don't want each topic to be just one word. Okay, so now this is the formulation. I just copy a bunch of things from different. So this is like a good lecture note. This is like textbook. This is like another textbook. They're all good illustrations. But what is important here is that you have additional loss term, which is called sparsity penalty, SSI. You want to minimize the difference, the KR divergence between something called row and row hat. So what is that? First, let's look at this term. You want to go through every neuron. So S2 is the number of neurons in the hidden layer. So for every dimension in your hidden representation, you want to minimize the KR divergence. The KR divergence between row and row hat. Row is our target sparsity. Hyperparameter, you want to preset. You want to say, I want the sparsity to be 0.1, and you minimize the difference between 0.1 and the actual one measured during our training process. And that one is actual sparsity, which is defined like this, which is essentially just sum up all the individual elements. They call it alpha j times x, alpha j of xi. Essentially, it's a function that maps this to this. So essentially, just sum up all the values and take the average. That is the sparsity definition. And you minimize their KL divergence. Why KL divergence? The quick reason is that the gradient property is nice. if you look at KL divergence versus MSE, it has neither gradient around the target sparsity. This is very bad. And this is very good. You want this
I'm sorry, I don't follow the detail. Can you go a little bit more step by step of what is how it is converted to KL divergence? I don't know that.
Yeah. So essentially, you want to minimize. Okay. So essentially, you want to have a lot of zero entries here,
Right.
rather than just count number of zeros. That is naive. People come up with this idea that they define this metric called sparsity, which is sum of all the numbers in this representation, all the activation value, right? And then take the difference. That measures how sparse it is.
So the smaller the value is, the better it is. Is that what it is?
Right, because you want that to be sparse. So if they are very high values, they are all like 1,000 or
Right.
just in the extreme case, it
Right.
will be very large. They
Right.
deviate from 0.1 a lot, and you penalize that.
Right.
So that is amazing.
So you want to minimize it, and then how is it KL done? So I see a sum, but I don't
Okay,
see
let
KL
me see.
divergence.
Okay, so essentially you want to have a target sparsity, one number, 0.1.
Right.
That is another number. This one number is another number. So you have two numbers. So why this KL divergence?
So what is that? Can you explain that formula? That
that
root
one?
formula? Yeah.
That is defined on a particular. This is average across. First, M is the number of. So let's focus on this first.
Right.
This is the M is the number of training examples. So this is average across a bunch of training data points.
All training data points.
All training
Okay,
data
yeah.
points. You can
And
think of
then
that.
what is AJ?
J is for any J there, right? Or here. J is individual neurons. So in this case,
Individual neuron.
you
The
have
hidden
1,
layer.
2, 3, 4, 5, 6 hidden neurons.
Okay.
So S2 is 6. So you go over each neuron.
Yeah.
Each neuron, you go through all the training sets, and you find this one's particular sparsity defined by rho hat
Can
J.
you, yeah, let me go over that a little more
Right,
carefully. So
right.
AJ2, what is that 2?
Square, I think, or something. Not totally sure, but I'll double check later. But probably, I think, in my opinion, I think it is the activation. A means activation of this particular neuron. Because it could be negative, so I think that's why they take the square. That's my thing. And you double check though, but
So
let's assume that.
let's say xi is the input vector.
Yeah.
Let's say, and then AJ2 is the whatever matrix that you multiply to the input vector to get the value of that particular neuron.
Right.
So once it's that is what the value that we get.
I think it's more like a function.
Right.
It's more like a
yes,
function
yes.
of x.
Or weight.
Yeah,
It can be a weight, a sequence of weights, that
Okay.
individual dimension. So once you multiply these two, you get that activation value, right?
Yeah.
And then once you get the activation value, we sum it over the entire set of
Training data.
training data,
Right.
and then you get the raw value. That is the part that I actually don't get very well. Why don't I get it? Because I think we may want to sum up first over the entire hidden layers, and then somehow minimize it, as opposed to sum up over the entire data set and somehow to minimize it. I
I
don't
think
really.
at the end they might. See, so difference is that the KL divergence is defined here.
Right. The KL divergence is what is rho. So here, now we know the rho J,
I is not the number of training examples, I is the number of inputs.
number of training data. I think
No,
that
I
is what
think
it
it's
says.
the number of
Which one?
inputs. The number of inputs is x1 to x6.
Here, those I. Okay, so this is another textbook. Sorry about the confusion of the notation. This x1 to x6, this is not the same as xi over there. Sorry, this is very bad. They together form maybe one xi, and this is the
Right, right,
individual dimension of that xi. Sorry about that.
I is a vector.
Yeah. Each x, the x superscript 1, they use superscript. See, x superscript. They want to differentiate between the subscript. Subscript is the index into this particular entry.
Then the A2, that's also superscript. That's why that
Right.
become a Korea. That's a square.
I don't know.
That's a square.
I'll check that later. But essentially, you can. The one thing I'm sure is that this is the activation value, but the exact definition I need to check later. Hopefully, that's clear. Because this is not nowadays very popular, so I didn't spend a great amount of time in detail. But I hope that you get a basic idea of that.
No,
This
I don't
is,
get the basic. That's the
Okay,
problem. I want
okay.
to get the basic idea. I
Okay.
really want to get the basic.
Yeah,
idea.
let's see. So this is actually two numbers, two scalars. Do you agree that, right?
No, I don't think that
No,
is two scalar. That is two vectors. It should be two
Yeah,
vector.
the KL divergence should be between two vectors.
In this case,
KL divergence should be a two vector.
Two vectors.
Where they have many layers. They have many. It's a very deep.
They just have this one hidden layer, so they're just doing that on this one hidden layer. This is one thing I'm sure. So let's start from one thing I'm mostly sure and think about this.
And then what is
I think in this case, it's
Yeah.
really, it is defined on probability distribution. I agree.
right?
But in this case, it's more like I think. Okay, so what is the KR? What's the basic definition of KR? You remember the mathematical formula?
Yeah, I do.
So
Yeah.
please state if you remember. It's actually.
The log of P of log of P of.
So what if it's a scalar? So what if it's a scalar? Does that still work? What do you think?
No,
No, I don't think so.
I don't think so because it have to be two distributions.
What if it's one number? Then does it have any meaning? No.
No, it's just one.
Yeah.
1 times log of 1 over 1. Yeah.
What if there are different P and Q? So it's P like log of P over Q, right? So that
P
is
and Q cannot be different because P and Q normalized should be
Yeah,
normalized
should be
to 1.
one. Should be two distributions.
Right.
Like normalized like.
I mean, in this case, I think what they want to do is that they want to define one number for the sparsity, and they don't tie. So the KL is more like, I think if you tweak it, it's more like measuring the. Okay, so their motivation is that we are not using MSE. MSE is not defined on probability distribution, right? MSE mean squared error is defined on two numbers, two scalars, right? They just want to use something better than MSE.
No,
better
but
gradient.
even for MSE can be defined on two scalars. For MSE, we can use it for measuring the distance between two distributions as well.
As well, but in this case, let's assume it's MSE is for two numbers.
Two numbers. Okay.
Assume that there are two numbers, not distributions.
Okay.
Let's assume that. And then if we plot it out, we find that if your target number is 0.1 and your actual sparsity is 0.01, the gradient is not big. Do you agree with that?
Okay.
Okay.
Maybe. Yeah.
Okay, so then they come up with some better difference metric between the two numbers, which is the not exactly distribution, but just the slight abuse of the term KL. You can imagine that then if you plot the function P of log P over Q over just two numbers, right? This is the result. So let's look at what it means. This is the target number, 0.1, and this is the actual number. And if you just do P of log P over that, you would be able to get something like that.
I see. So what you are saying is that here KL divergence is not really the traditional definition of KL divergence. It's just a formula that we use.
It's just a formula.
Which is exactly the same formula that we use for the KL divergence for individual dimensions of the probability distribution.
Yes.
So here, if you have, let's say, rho j,
Right.
then rho j, we compute the rho j that way, and then that is a single number.
Yes.
And then there is this rho value that we use as the goal function,
Right.
or the metric that you want to optimize for.
Right.
So what you do is we compute the rho times log of rho hat,
Yeah. Just
and then
like
that is the formula that we try to optimize.
Right.
I see.
So those smart people just think about why not just somehow change the basic definition of KL a bit. Just use this, let's say, element-wise form.
Right,
just
right.
P of
But
log.
this is not symmetric definition.
This is not
Okay.
symmetric.
Not symmetric.
Right.
Yeah, you are definitely correct. This is still not perfect, but they claim that it's better than the symmetric one. So this is symmetric. Do you agree? This is like a standard curve which is symmetric around 0.1. The MSE. Do you agree? This x minus 0.1 squared. Right? If you recall high school mathematics, that is symmetric. That is good, but they have worse gradient property. But back then they want to have better gradient property. So that is the
I have a question. So why does KL using that particular formula somehow enforces sparsity?
because you have some very low target sparsity 0.1. See, if you have very high activation here, you'll be not 0.1, you'll be something very big. You normalize it, so it's between 0 and 1, first of all. You sum them up and you make sure that it's between 0 and 1. If this is not sparse, the result would be toward this end.
So here then the reason why we are using KL divergence, it is
Faster,
not right.
steeper,
It's just
lower.
a mechanism to enforce that the training time is much faster
Yeah. Training
than
time is
using
faster.
some other.
Right.
So that is your understanding.
Just small
Okay.
trick. Yeah.
Can you explain why KL divergence is being used for inducing sparsity? So as I see, there's a square term over the weight vector, the weight.
This one, right?
Yeah.
Okay, so this is something I'm going to explain later. But let's explain now. So we actually have three terms. This is a reconstruction error, right? We know it already. This is a regularization term where we prevent overfit by penalizing the value of the weight matrix This is similar to what you do in least square estimation. You introduce this regularization term.
And don't we want to induce the sparsity in the weight matrix?
So reducing the size of the weight matrix could lead to reduced activation because weight matrices are not that same. W times X equal to the activation. If W is small, hopefully the activation will also be small. So your question is why is this already enough, right?
Also, why do I need a square? So as I
Yeah, why do
understand,
you need a square?
yeah, it should just be a WGI because as I understand, L1 norm is enough for inducing sparsity. L2 norms are.
So your question is why this is not already enough?
We're having a simple sum of over all these values, WGI, not square, just WGI. Because
Also, the answer I think I can provide is that usually when you add a regularization term, unless you really want sparsity, you just use the F2 square, the F2 norm, most of the time. Has much better property in many cases. So in this case, their goal is not to make that weight vector or weight matrix sparse. That is not their goal. Their goal is to make that hidden vector representation sparse, right? So the claim is that the KL divergence term will make that hidden representation sparse. This regularization term, because our goal is not to make that weight matrix sparse, we just use the square. I think that is what they are trying to do. But if you wanted to make the hidden weight matrix also to be sparse, then you have to use the F1.
So this is the reference I got. It's written by Andrew Wu, so from Stanford, this class. You can read it more. It's a great tutorial with better explanation than here. But thank you very much, Professor. Okay, thank you for questions as well. Any questions? So if we go back to the basics, it's just trying to penalize the activation. Okay, and they find that they get better result. Later in 2013, some people propose something better. So this is one downside of this model. This results in sparse activation of hidden units across training points because the average are according different training points. There's something related to your question before, but it does not guarantee that each input has a sparse representation. So it's more like average across all training points, but it does not for each input it has sparse. So it's not very strong guarantee. So that's why people propose something better, which is agree as well. So this is just a very crude model back in 2008.
No, the better one, what do they do?
Not sure. I only read the basics. So you can encourage
I thought you were
learn
going
more.
to say, what's the difference of the better?
No.
The better?
Again, there are many different models, and I need to prioritize which is more important.
You're
Hopefully
doing
I
an
understand.
excellent job.
Okay, thank you. Yeah,
We are asking all these questions because you're doing an excellent job.
Okay,
You have
thank
done
Since in the paper it says it's trying to calculate the KL divergence between two vectors, but the two vectors are composed of several row and row j.
So individual element wise, it's like that, but you
And the
can
number
imagine.
of row I and row j is the number of hidden units.
So together, you can imagine this as a probability distribution. If you sum up, so this whole thing together is the probability distribution. Okay, thank you for
Yeah,
pointing
so
out.
it's still
So there is a probability.
It's still the KL divergence.
of two vectors, but the vectors have the same numbers inside.
So basically just the KL divergence between,
One
That
vector and
vector.
another vector.
okay.
Yeah. Another vector is all 0.1, not 0. I
The
think the other vector is all 0.1 even.
Yeah, the number of the vector is the number of the units, hidden units. It's
Okay.
S2.
Okay, so thanks for pointing out. If you want to learn more, you can read the lecture note as well. And here is the results. And as you can see here, it doesn't do a very good job on reconstructing the input. It's blurry than the original one. Here's a feature they learned.
How
Okay.
many dimensions did they embed it into?
I need to check this textbook.
Ah.
This is more like buried in one of the TensorFlow code, one line. I need to check that though. But anyway, this brings up the issue of how to interpret or visualize autoencoders. Like I said, it's very simple. You can just visualize the weight matrix like this, right? And each one is a feature detector. However, in the case of text or graph, there's no natural meaning of the weight matrix. Right? In the image, it's fine because this multiplied by this element-wise, and you sum them, right? But in the case of text, no such meaning. So you can do something like this. You can treat each neuron as feature detector again, but to find which feature this particular neuron is detecting, You feed a random input, say an image or some text, and then you measure the activation of the neuron, a particular neuron you're interested in, just like what we defined before, some sparsity metric. And then you perform backpropagation to change the input so that the activation will be even higher. You want to gradient ascent. So you tweak this again and again until you get until you stabilize this, and then you get this works well for image case, and it may also work well for other cases. So we need investigation in that. This is just a potential thing one could do, and this is mentioned in some of the textbooks. Any questions? Okay, if not, I think we can move on. Later models, some of them I will emphasize less. So you will see this one, denoising autoencoder, also in 2008. The task is very simple. You want to denoise the image, right? And sparse coding could also do that, by the way. Just the previous model could also do that, but there's better motivation or better way to do it. In this case, it's more natural. Why it's more natural? Because you add a Gaussian noise to the input. Input is the same. Just add Gaussian noise and then feed into the encoder. And you want the decoder to remove it. So you reconstruct the same. So everything the same. This is still output minus x in the implementation level. But the only thing different is to x plus some random Gaussian with the same shape as input. But that is only difference. Hopefully it's simple to understand. And it achieves good result. It's more natural and it achieves better result. See here, the Gaussian noise is removed. And here the salt and pepper noise is also removed. Salt and pepper means some dot here. It's a good analogy to real world salt and pepper. And that is removed. Okay. And at the research level, I'm not going to detail, but I encourage you to read this good textbook, giving you a probabilistic interpretation of what's going on. So behind the scene, you can imagine there's a probabilistic graphical model. And there's something called a gradient field, which means that, okay, so this I can explain more in detail. If you have a point, this is a real data point, and you add a Gaussian noise. So because you train this for a lot of iterations, you would add different Gaussian noise because it's random Gaussian at each iteration. So you will have a bunch of points within this circle. It could potentially be infinity, but Gaussian, you know the Gaussian distribution. So most likely it's in this circle. And the decoder's goal, task, is to map it back to the curve. And this is done for every data point. So you can imagine that in this space, in this inputs-output space, if you slightly add some noise, you would get this. But the decoder would map it back to the real image. So that is so it's a better visualization. And you can read more, but I'm not going to detail. Essentially, this is equivalent to this is just another probabilistic way to write down this. If you don't understand why this is equivalent, I encourage you to recall least square estimation is the same as MLE under a Gaussian model. This is what we learned in basic machine learning courses. So they are equivalent, but I don't have time to go into details, and I encourage you to do that by yourself. So if you want to do research, you want to look at it in research level, you need to understand this. Any questions? If not, that's pretty much it. Okay. Read more of this? Okay.
No. Yes, I just.
Okay. It's okay. Yeah, so this is essentially the negative level. Yeah. So you want to minimize this. You want to maximize the data loss output. So minimize the negative of data loss output. And this whole thing is that this is the noise distribution, and assuming it's Gaussian, right? Given the real data, the noise is from a Gaussian.
So here we are trying to maximize the, as you say, log likelihood of our data, generating our data under that model. Is that correct?
Yeah.
That is to maximize that. Yeah. And then you are claiming that that is equivalent to that.
But you need to
square.
You need to think more. Okay. Thank you. That is basic setup. I just want to bring that out. And next is a contractive autoencoder. This is why we're very brief, just one slide. This is similar. This is what actually Zoe's question was. He asked what that small derivative means. This is what it means. It tries to resist infinitesimally small perturbations of input. This is original input. Right? Infinitesimal, let's make it clear, right? Infinitesimal small, right? If you take the derivative of the fx, which is the encoder function, with respect to the original input, and then you take the f norm, which is the central element wise summation, and then you take the square, this norm square, and then you have some hyperparameter lambda, you add this to the entire loss function, you minimize this, then you achieve this thing. If you slightly modify x, the encoder function, so say you have two very similar inputs, maybe one is the noise version of the non-noise version. They are very similar X. Because you ensure that derivative is small, the latent embeddings will also be similar. In this case, you see you have 3 data points, X. Ideal case, you do the identity function like Joey said. It's just identity mapping. But you penalize this derivative so that you will end up with something like flat term here. Then if you have some slight variation, perturbation, your latent embedding would be the same. Of course, there's problem like this jump here. So that is not perfect. And actually, this one, CAE and the denoising autoencoder we saw before, they are equivalent under certain conditions. You can also learn more here.
What is DAE?
Denoising. So it's the previous one, denoising.
Denoising.
Yeah. So this thing here and this thing here, derivative here, are equivalent. If you somehow assume Gaussian, assume some property, and you do the math, they will end up being the same. So this is another one in 2008.
Can I? The omega there, so what are we trying to do with that omega?
Minimize it. This is the last term. We minimize
We want
the
to minimize
derivative and you add this back to the reconstruction. Yes, that's it. So very simple regular writer, just. But it's hard to come up with this idea. Like implementation level is simple. That's what I mean. Okay. Different techniques. Another smart idea in 2011. Sorry, this is 2011. I need to correct that. Okay, another idea also in 2011 called the convolutional autoencoder. You can
I just want to mention one thing regarding the
sure.
previous one. So if you think about any gradient descent algorithm,
Right.
gradient-based optimization, what we try to do is we try to follow the gradients until when? Until the gradient becomes 0.
Yeah.
So gradient-based algorithm, essentially what we try to do is that we actually try to minimize the gradient. We try to put the gradient to be 0. That is when we start.
Okay, because we use this.
So in some sense, yes, in some sense that is what we do. Here, even though we say, here actually we mentioned it, CA and DA are equivalent under certain conditions.
Right.
When we actually think about gradient descent or gradient-based optimization, we are not only minimizing the original loss function, we are also trying to minimize the gradient as well.
Interesting.
Yeah.
So this is explicitly minimizing.
Right, explicitly minimizing it as opposed to implicitly minimizing it.
I see. But in order to do it, you will also want to minimize. If you think this as a function, loss function, you will also doing back propagation,
Right.
gradient descent on the gradient.
Right.
Gradient descent on the gradient.
Right.
Okay, interesting. Okay. Another interpretation, good. This one you can infer from the name. The idea is very simple. Just replace multi-layer perceptron or fully connected layer with convolution layer for image. That's simple. But they can do some cool applications because convolutional neural networks plus pooling layers, together they are better at extracting features. That's something we all know. So they do something called super resolution. The input is the low resolution one, the high resolution one. So essentially it's also denoising. It's just another fancy way to say denoising. But besides that, they could also do something like image coloring. You have some old picture, and you want to make it colorful. Black and white turn into this. And you train the autoencoder, so it learns that this part should probably be sky and should be blue by looking at a lot of different non-labeled images. And so now you have a new image, your own image, maybe. Then you can do colorization like this. So they are just cool applications. So inspiring.
Do you know this very well?
This is something I know from here. So
So
I don't have
the. Can you go back one slide? Do you understand what this means, well?
I understand it, everything here, but other than that, not all in detail. I can give you high level.
Yes, please.
So so in this part, they call it patch extraction and representation. They have convolution filter F1 by F1 across this image. They detecting features for this low resolution image. Then one feature maps of low resolution images. Okay, and that's stored here.
So that is nothing more than
Just-
the convolutional filtering.
Not more than that, just
Yeah,
convolution and
Okay. And then after that, what do we do?
reconstruct, and then they do nonlinear mapping from low resolution image feature maps. Actually, the features of the low image map it through some nonlinear layers to high resolution images.
Oh.
So how? That's
I
something
see.
I don't know. That's something I need to read.
I see. So they have a pair of input where
Okay,
they have a
okay.
low resolution image and they have
And
a
they
high
make the
resolution
connection
image.
through here. Right? They
And
learn
then
that
somehow they learn the
mapping here.
features based on
yes.
the low resolution images. And then from there, somehow they try to come up with a weight matrix that somehow reconstruct the high resolution
Yes,
image.
yes.
I see.
Through all through backpropagation because they have both the
Right.
bad and
Those
good.
are okay. Please.
Yeah. So that is the intuition. See, nonlinear mapping to higher resolution patch representations. The last layer combines the prediction with a special neighborhood to produce final one. So you need to reproduce that somehow. Reproduce part. That turns out to be important actually. The reconstruction part for graph is usually harder. If you think about it, it's an unlabeled, undirected graph. How do you reconstruct the original graph? That could be a hard question, research question, and we'll see later, hopefully. And the next one is recursive autoencoders in 2011. This is proposed by Angela Wu as well. Okay, cool, no problem.
Just this one.
Yeah.
So here, coming up original and then bicubic, whatever they are doing much better than bicubic. That now I understand because that is how they train on, right?
Right.
But this part, somehow adding the colors, how is it related to that one?
You can imagine that you have your output is the colored version rather than, in this case, it's a noise-free version.
Oh, I
It's
see,
a
I
colored
see.
version.
They applied on the black and white and then color version, and somehow it automatically. Oh my
Because they know
God.
that the sky should always be blue. They look at a lot of such beautiful pictures,
Right.
and they realize, okay, sky should probably always be blue, so map it to blue. That's what they do. They learn that mapping. Yeah. So that's what I.
Magic.
That's what I feel very magic. So yeah, you can learn more here. Okay. Okay. Next part is recursive autoencoders for NLP tasks mostly. So
May I ask one more question?
okay, sure.
Did they give any insight about exactly what they learned and why this is happening? No, they didn't
This
give.
is a very shallow blog, not just very reader friendly. You have to read actual paper, which there's a link, but you have to click that and read it. But I don't read it, so I can't give more detail, unfortunately. But yeah, but you can read more yourself later. Recursive autoencoder, as I said, it's essentially for NLP tasks. Before I go into details, I need to say that this is for sentence level embedding. You have a bunch of words. I walk into a parked car, and you want to try. I want to classify this as a positive, negative, neutral sentiment. And the key insight is that you can't just use average bag of words because there's dependency. We all know this nowadays. They are very different. If you change the order, blood cells destroying infections, very different from infection destroying white blood cells. Very negative and very positive. Oh, sorry, very the other way. But anyway, you get the idea. So you can't just use average aggregation. You have to use something better. For example, STM. But back then in 2011, they proposed this one. And actually, this one, the paper is Professor Cho assigned in the CS249 course. So if you take that class, you will learn more in that presentation as well. Dynamic pooling and offloading recursive autoencoders. This is a variation, it's an extension of this one. So basically, in this case, you have two words. At the lowest level, you have individual words, and you move up level by creating some intermediary representation for those, just for those two words called Y1. And your encoder is this part, and decoder is this part. You are trying to minimize the error. So you successfully, hopefully, after this step, you successfully learn a good representation for those two words. And then you move up level. You incorporate the third word and use the third word and the previous two words representation to learn. Because you want something regular, you want just two inputs and two outputs each time. You don't want to incorporate all of them. That is their idea. So then you just use the previous two's representation Y1. You do it recursive until you reach the top. So this will be the final representation for the sentence, and you feed that into classifier.
Why you want to do it in a reverse order?
Sorry?
Why you want to do it in a reverse order?
Good question. This is the one thing they've improved later. They could use parse tree, like NLP parse tree, we all know, right? And then based on this parse tree, you can get a better sense of what should be grouped together rather than just randomly guessing or random heuristic that is the last two. You're right. Yeah, it's 1, 2, 3. It's this way. 1, 2. This is the forward order. 1, 2, 3, 4. So the forward order. But anyway.
I1 is for example, the first word in the sentence.
Yes. I, for example, I walked into somewhere. This I, and I walked. First group I walked, and then I walked into, and then I walked into somewhere. This order. But you could use parse tree. That's an improvement on the hopefully that's clear. And you could use many different layers rather than simple MLP. You could also normalize it to prevent some exploding because you are essentially doing this recursively. You could also introduce some supervised laws here for other tasks, for freeze level tasks maybe. And here you could predict all children and their needs rather than just reconstructing the previous one. This is very vague, but I encourage you to actually attend that presentation in CS249. You'll hear more about what unfolding means in this case and what dynamic pooling means. You could also penalize top-level nodes more heavily because they contain more children. Right? So those are the
I
basic.
have one question.
Okay.
So whenever we merge them together and then encode them, do we use the same encoder for every single?
The encoder is here, yes, WDP plus BD. Right. So it's the same W. Right?
What is P? What is P?
P is parent, D is something else. But anyway, I think the answer is yes. But
Yes,
let's
yes,
forget
yes.
about this. I think that
They use the same function.
okay. Any other questions? Okay, we still have time. It's
I
fine.
have one more.
Okay,
question.
sure.
Did you read this paper very carefully?
No, I defer that to your wonderful class. I know.
Not yet.
I defer that to the
Not yet,
class.
okay.
I know that
You're
I
a science student.
Yes, I am science student.
The full size student.
I don't remember.
I have to look at it later.
I'm not, but
Not someone sitting here, right?
not sure. Okay. Okay. So variational autoencoders is a very popular model. So this deserves more careful presentation, I think. So the intuition is this. Let's think about previously we are sort of transforming input to some P representation. And it's deterministic most of the time. You could add some random noise. But even if you add random noise, in this layer, in this encoder layer, once you add random noise, everything will be fixed. It will be deterministic. You have one number every dimension, representing the latent attribute, right? So this guy is 0.99, smiley, yes, and 0.85 something else. So this is the previous one. Let's look at this. Any questions? And then the intuition is that why not just output some non-determinist statistical distribution for each dimension? So smile, we are not saying this 100% smile, we are saying this most likely smile around this mean, and then we have some variance. So we essentially output two things. We output the mean and the variance. We assume there's a Gaussian distribution. So you see, we are assuming a Gaussian prior on this latent space. This is a very key intuition. So encoder output static distribution, and when in the decoder part, you would randomly sample something according to the mean and the variance. You randomly sample the orange one, and next time you randomly sample something else, say the red one. They are different into decoder, different samples in the decoder. And you hope that no matter which one you sample, you can get back the original same image. So this way you explicitly enforce that the similar images or the same image would get the same embedding in the embedding space. That means if you have very close points in your embedding space, they would have essentially very close or the same corresponding image. That is something explicitly enforced through this sampling process.
I have a question. The smile. I either smile or not smile.
Right, okay.
So,
You can smell halfway.
so my question is, do you really need standard deviation and the mean? Maybe what we can do is that we kind of assume a smile is a binary variable, and then the probability really shows us how confident we are regarding either of these two extremes, right? So
That is the previous one, the confidence score of 0.99.
right. So there, now when we decode it, instead of directly using that, now what we do is we take a sample using that probability, and we sample either smile or not smile, and then we somehow generate the output.
You need to be concrete on what you mean by sample whether smile or not smile, because you can imagine there's one extreme 0,
Right.
not smile, and 100%.
Right.
So how do you sample it?
So the way that we sample it is every dimension, we take a sample value between 0 and 1. And 0 means that it doesn't happen, 1 means that
Uniform
it does.
distribution or?
No, it's not uniform, it's based on that 0.99 probability. So if it is 0.99, then with 99% probability we smile.
You will sample 1.
We sample 1, yeah,
Okay.
just either 1 or 0.
Or either one, 0.
And then
Okay.
which one I pick based on that probability.
Okay, that's another way. Okay.
First of all, are these? I don't think these are probably scores. These are some scores, some latent representations. I think there's minus
Could be
0.7
negative. But you could normalize somehow. But as you said, yeah, you can't guarantee that every element in this vector is between 0 and 1, unless you do some trick. That is another
The
potential
reason
problem.
why I'm kind of saying that is because I have some fundamental conviction that
Oh,
everything should be 0 and 1.
Okay.
That is somehow what I think the world is.
Okay. I think you can. Yeah, maybe there is some paper doing that, or you can investigate that more,
Okay,
or we can
anyway,
discuss
thank
more.
you,
Yeah,
thank
good.
you.
Good for pointing that out, for sharing
But,
with us.
like, there are some of them are binary, right? Go to the distribution. But
This
some
one.
of them are not binary, right? Like high color, that's
Binary?
do that hair color. lots
Hair
of-
color. Okay, so
They're not.
Hair
How
color.
should I interpret that distribution?
with this, so Gaussian distribution is like with high probability you will return the mean.
Of
Yeah.
what? Like hair color is what? Like it's a. The hair have some color, right?
Yeah,
so
yeah.
then how do you represent here? Like non-binary features.
Oh,
How do
so-
you represent that?
So you kind of embed it. It's so intuitive. I think the answer is that you could have many colors: red, black, anything, yellow. So this is continuous. If you imagine the color should be continuous by pixels.
Maybe that
Right?
represents
Represent the color
the
spectrum.
intensity in red and maybe green and blue.
Yeah.
I see. So RGB.
Yeah, RGB. Yeah.
RGB.
Maybe, yeah.
Spectrum, something like that. Okay. So it gradually changes. Everything's so the key idea is smooth. They want everything to be smooth, right? Sorry, this is like different
Yeah, yeah, yeah.
intrinsic
No, no, no,
intuition,
I
but let's
I'm just very
Yeah, yeah.
curious.
max values paper. Okay. So then they expect an accurate reconstruction for any sample from the latent state distribution. So they try to make them close. What's the advantage? As I said, there are some reasoning. So first is that you can generate new data because once you learn this distribution, now you have a good latent space with all the existing training samples embedded as data points in this latent space, and then you can randomly sample something. Just pick a point according to this distribution. I will show you in picture later. And then you can use the decoder to generate a new data. You can also do this for the previous ones actually. But there's a fundamental problem with the previous ones. Let's see. So let's go here. This is better. So previous ones, if you only have the reconstruction loss, they experimentally verify that you will have a lot of holes in the latent space. That means if you randomly pick a point just here, and you reconstruct it, it will be not similar to any of the existing ones. It will be bad quality image, some garbage. And now if you enforce the Gaussian distribution, you have several well-separated clusters. And not that well, but they are still clusters. And they've experimentally verified that it occupies the space nicer. So you have less holes. And if you sample something from here, it's very close to the picture, the image with digit 1. And here is very close image with digit 2. And if you draw a line here, you do linear interpolation, you move from this picture to that picture. And for every point as you move, you decode it, you reconstruct the corresponding image. You would get some smooth transitions between the digits. 6 gradually translates to 0, gradually translates to 4, 0 and 4, and then 4 becomes 9 at the end. So hopefully you can see that there is some smooth transition between that. That's what people want for data generation, for new data generation. This is the key intuition, I think, in this presentation. You want to learn smooth latent representation of the input data, which is good
I
for
don't follow this
yeah,
particular
so
graph.
it's fine. I don't expect them to everyone immediate guidance. So that's why I want to pause it for now. So it's good for interpolation, sampling, generation, downstream classification. Let's understand the easy way. If you do something like this, and you also have something like that, let's forget about generation. You just want to classify different images. So you have two-stage
First,
pipeline.
Let me actually ask
Yes.
my question.
Okay.
So only reconstruction laws and only KL divergence
Right.
and combination, that label seems to indicate that our training is done differently.
Yeah. So
And
let me be
different
clear.
laws
Yeah.
yeah.
So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you have 0, 1, 2, 3, 4. You have essentially 10 different kinds of data in your MIS data set.
Right.
Handwritten digit.
Right.
So that is the simplest one. So you
Right.
have 10 clusters.
Right.
That is the simple idea.
No. So how only reconstruction laws? So the way that these three graphs are generated are based on different loss function.
Right. So this loss function, yeah, this is only using the reconstruction error, the MSE between the output and input that you see before.
Okay. And then what about the second one? Only KL divergence.
That is something I have to show you later. I deliberately skip these two slides because this is what I need to show in great detail later.
Oh,
But you can just imagine you do something else, but then this is the final result of combining them.
Right.
I want to first talk about the goal. What is the final
I see,
objective
I
of
see,
it?
I see.
Because it's the motivation.
I see. Then how is it related to variational autoencoding? This has nothing to do
Variational.
with that.
Because the KL part, part
Okay,
ensures variation,
okay.
which has nice probability interpretation, which uses variational Bayesian inference, which I'm
Okay.
not expert on, but I can show the basics.
Okay, good,
Okay,
good.
so that is the part. Okay. After that, do you have any questions on the goal we want to achieve? We want to achieve this nice Gaussian clusters. And how to achieve that? Through KL divergence. Yeah, so we need to then we need to look at KL divergence. But this is really the key before you look at the details, because once you have that, you could do some music VAE, which is some Google project released very recently, where artists can create new music by clicking on the screen. Because if you click on random point on the screen, corresponding to clicking some random point, sampling a random point, they say that the desirable property for latent space can be summarized first expression. Any real music should be mapped to some point in latent space. Second, realism. Any point in latent space should be mapped on some realistic music. It shouldn't be garbage. Third is the key point, the smoothness. Examples from nearby points in the latent space should have similar qualities to one another.
Is this way to get around copyright music? Yeah, essentially similar music, but not that one. So.
Right. So essentially, to give you a feeling why this idea of smoothness really work, I can. Okay, that's fine. I can try to. I see. I can just first, and then it will be this. Hopefully you can see that, and then you can. So this is the original one. A bit louder, and then you can. No, if you can draw it. You can do some interpolation here. It's not noise, but I'll make it smaller. Yeah, so as it can be tended, you will get high quality output no matter where you are. So that's the property of that's the smoothing property. You don't have some pulse. Everything's smooth, and you don't have some weird transitions. Another way is you can add your corners. So you can add different things. I don't want to use this sound system. It's not this fault. It's actually the sound system of this room. But anyway, you get the idea, so we can come back. So hopefully you see why this is the